Today's video will look at determining the chemical formula of a compound from numerical data. Title: Empirical Determination of the Formula of a Compound, where empirical refers to a mathematical determination. One type of chemical formula that we can deal with in chemistry, it's a major concept, is an empirical formula. Empirical formulas consist of the symbols for the elements combined in a ratio, and a ratio that gives the subscript showing the smallest whole number mole ratio of the different atoms of the compound. So when we look at an empirical formula, we can say something like, if we have, let's say we have calcium and bromine. The empirical formula may be something like CaXBRY, where X to Y is the ratio of moles of calcium to bromine or bromide, and it is the simplest ratio. For that reason, empirical formulas are sometimes called simplest formulas. So as an example, let's suppose that we have a compound, and it's 20 total grams of compound, and it's analyzed to determine its components. Calcium and bromine are the two components, and analysis of this 20 grams indicates that there's 4 grams of calcium present. What's the empirical formula for the compound? Well, if we know we have 20 total grams of compound, and we have 4 grams of calcium, then that must mean that there's 16 grams of bromine present, because 16 plus 4 is equal to 20. Now what we're really trying to find here is the ratio of Ca to Br. So we're trying to find the X, one more time, the X to Y ratio of moles. So to do that, we're going to convert our masses of element into moles of element. So to do that using our factor label problem solving that we've been doing for a while now, we can say that in every 1 mole of calcium is 40.1 grams. And for every 1 mole of bromine, there's 79.9 grams. That gives us, for the calcium, 0.0998 moles calcium to 0.200 moles of bromine. So technically we've got Ca 0.0998 Br 0.200. But obviously that's not a typical chemical formula. We've got to have simple whole numbers. So the easiest way to determine the whole number ratio would be to look at the two values that we have, 0.0998 and 0.2, and we're going to reduce by dividing by the smallest. 0.0998 is smaller than 0.2, so we're going to divide by 0.0998. Same thing here, 0.0998. What this gives is 1, and this is probably very close to 2. Goes up to 2.00. And then there's also a 400 following that, but it's very, very close to 2. So 1 to 2 ratio. So our X to Y ratio is 1 to 2. This means that we have calcium with a 1, Br with a 2. 2 coming from here, 1 from here. This would be our empirical formula. This is also an ionic compound, so since this is an ionic compound, it's likely that the true formula, not just the simplest ratio, is CaBr2, because ionic compounds are written in such a way that we have a simplest ratio. In our next problem, very similar problem, we've got an analysis of 10.150 grams of a compound, and that compound contains only phosphorus and oxygen. And the analysis indicates that the phosphorus content is 4.433 grams out of the 10.150 grams. We want to know the empirical formula. So again, we're looking for number of moles of phosphorus to number of moles of oxygen. So we start by saying we've got 4.433 grams of phosphorus. And since we have 10.150 grams minus the 4.433, that means we have 5.717 grams of oxygen present. So we need to convert to moles because we're looking for this XY mole ratio. And to do that, same standard problem solving style. We want grams phosphorus over moles phosphorus, or moles over grams. 1 mole per 31 grams. And 1 mole oxygen over 16 grams. Dividing 4.433 by 31 gives 0.357. 3 moles phosphorus, and for oxygen 5.717 divided by 16 comes to 0.357, 0.3573 moles of oxygen, and this is incorrect. I actually wrote down oxygen's number here. This is 0.1430 moles of phosphorus. Finding the whole number ratio, we divide each of these by the smallest, 0.1430 moles. It's going to give us 1. And then this one by 0.1430 moles. Gives 2.5. Okay, so we get a 1 to 2.5 ratio. That is not appropriate still. We have a fraction. So we have the fraction, we actually have 2 1/2. We want to clear this fraction to make it the simplest whole number. The way we do that is we look at the denominator of the fraction, and we multiply everything by that. So we've got 2.5 times the denominator times 2 equals 5. So we're going to have to multiply each of these by the number to clear up this 1/2, which is 2. So 2 times 1 is 2, and 2 times 2 1/2, 2.5 is 5. That is a simple whole number ratio, so we have P2 0.05. In the future you'll see other fractions, but it's always done the same way. Multiply by the denominator of the fraction. So if you have something like 1/3, multiply by 3. If you have 2/3, multiply by 3. If you have 1/5, 0.2, multiply by 5. And that will take care of the fraction for you. So final answer, P205. Now, often when we're finding composition data, what a compound is made of, we actually determine percent composition in a laboratory. So often we're presented with percentage composition data. So in this case we've got 26.56% of a compound is equal to potassium. And we've got 35.41% chromium. And then we also have some oxygen. Remember that everything has to add up to 100%, so if we would take 100% minus 26.56% minus 35.41%, that's going to leave us with 38.03%, and that would be oxygen. So 38.03% oxygen. Our issue is that we don't have a way to directly convert percentages to moles. So we have to know the size of the sample that we're looking at. Remember the law of definite composition. Law of definite composition says that the percentage by mass of the elements in a compound is always going to be a constant. So it doesn't matter what size sample we choose, the percentage is always going to be the same. So for these percentages, we can take any size sample we want and determine these percentages of that size sample. Now, and that's any size that you want to, any number that you choose. However, if we assume a 100-gram sample, the problem becomes very easy because 26.56% of 100 is equal to 26.56 grams of potassium. 35.41% of 100, that same 100, is 35.41 grams of chromium, and the same holds true for the oxygen, 38.03 grams of oxygen. Assuming a 100-gram sample makes the problem much easier. So then percentages are just converted directly over to masses in grams. We now convert just like before. Once we've got masses, we're going to convert to moles. 1 mole potassium, 39.1 grams. 1 mole chromium, 52 grams. And 1 mole oxygen, 16 grams. The values we get for this are 0.679, 0.6810, this is moles potassium, moles chromium, and then 2.377 moles of oxygen. Then to get our whole number ratio, we're going to divide each value by 0.0793. And that equals 1. Those are 6's, not 0's. This is also going to round to 1. This rounds to 3.5. We have a fraction here, 3.5, so we want to clear that up by multiplying everything by 2. Because 0.5 is 1/2. So that's going to equal 2, 2, 7. So this becomes K2 Cr2O7, which is probably potassium dichromate. Don't forget to clear the fraction at the end. In our next problem, we again have percentages. So the second example of that, we've got a compound that contains 63.52% Fe and 36.48% sulfur. And first thing that we would want to do is convert our percentages to grams by assume 100 gram sample. If we assume a 100 gram sample, then this is 63.52 grams of iron and 36.48 grams of sulfur. Then go through the same process, convert grams. Once we have mass, we convert to moles. 1 mole of iron, 55.8 grams. 1 mole of sulfur, 32.1 grams. In this case, we get 1.138 moles of iron, and here we get 1.136 moles of sulfur. Divide each by 1.136. One to one. So the formula FeS. 1 iron to every 1 sulfur. Now let's look at the determination of the formula for a hydrate. We've got a mass of copper 2 sulfate, which is blue and hydrated. It's placed in a crucible and heated. After heating, we have 1.59 grams of anhydrous copper 2 sulfate remaining. What's the formula for the hydrate, and name the hydrate? Okay, first of all, the term anhydrous. Anhydrous means without water, or dry. Very similar to the term dehydrated. So we've got copper 2 sulfate, so we actually know that we have CuSO4 dot in H2O. What we don't know is how much water. So what we're going to do is we're going to heat the copper 2 sulfate hydrate until the water leaves. The water still has a boiling point of 100, even though it is attracted to the crystal, so it may take a little more energy than that to cause it to separate, but it vaporizes, and you actually even get a color change in the crystal from a nice shiny blue to sort of a white-gray crystalline substance that would be remaining behind. So in this case, what we're looking for, I'm going to put an X here, we're looking for the X to N ratio. This would be moles of copper 2 sulfate to moles H2O. And this is, in hydrates, this is always going to be a 1 to something ratio. And N is a common letter to use to stand for moles. So we've got 2.50 grams CuSO4 dot N H2O. We heat it. After heating it, we end up with 1.59 grams of CuSO4, no water. That's the anhydrous. So the difference between these two masses is the water itself. So we can find out how many grams of water by subtracting these two. That's 2.50 minus 1.59. That gives us 0.91 grams of water. Okay, so we now have two values that are of interest. This and this, the masses of the individual parts. All right, so we want to convert our 1.59 grams CuSO4 to moles. 1 mole CuSO4. CuSO4 is 63.5 grams per mole, 32.1 grams per mole, And this would be 16 times 4 would be 64 grams. So that gives 63.5 plus 32.1 plus 64 adds to 130.6. That is not correct. I have a wrong number there. 63.5 plus 32.1 plus 64. That is 159.6 grams. So that's 1.59 divided by 159.6. That gives 0.00996 moles CuSO4. And we have 0.91 grams of H2O. We're going to convert that to moles also. And H2O, we've got 1.01 times 2 is 2.02 grams. 16 grams, 16 plus 2.02 would be 18.02 grams, 1 mole. So 0.91 divided by 18.02, that's 0.0505 moles H2O. So instead of finding moles of the individual elements, we're finding moles of the parts of the compound, the ionic copper 2 sulfate and the hydrate out here, which is the water. We're going to divide each of these by 0.0096996 moles. Same here. This is 1. This is 5. So we end up with 1 CuSO4 dot 5 H2O, which is copper 2 sulfate pentahydrate.